Hello everybody. So what we're going to be looking at today is basic definite integrals. So you learned about indefinite integrals previously. So just a reminder, indefinite integrals. They looked like this, right? And what you were doing when you found an indefinite integral is you were just finding an antiderivative, right? You just find antiderivatives. And that's all an indefinite integral is. So a definite integral, first of all, you have to know what it looks like. So definite integrals. They look like this. So it's still the same symbol as an indefinite integral, so that's the same. What's different is there's an a and a b here, and those are typically going to be numbers, but not always. Okay, and so that's what a definite integral looks like. And what it is, well, let's talk about it, right? That's what we're going to be doing. So that's a definite integral, that's the symbols for it. And by definition, it is as follows. So actually, it's a little bit tricky to write the precise definition down. So I'm going to write a definition that would give you the definite integral, but yeah, I'll write a definition that would give you the definite integral, but it's not like it's not a perfect definition. And yeah, before we do that though, let's look at a picture, because the picture really will help see what's going on. So you have an a and a b, and they're here on your x-axis, and you have a y-axis, of course, and then you have your function. Now your function is just any kind of function here, okay? And if you take this function and you draw these lines in here like this, and then you shade this area, the area is between the curve and the x-axis here. That area is actually the definite integral, okay? Yeah, and that's what it is. So that area is the definite integral, but that's only going to be for a positive function. So I'm going to write it this way. I'm going to say if f of x is positive, or at least non-zero, above zero, so non-negative. So if f of x is non-negative, then the definite integral of f of x from x equals a to x equals b is denoted, well, the symbol that we already talked about, denoted as follows, like that, and is equal, its value is equal to the area under the curve y equals f of x above the x-axis and between x equals a and x equals b, right? And so that's what I drew on the picture there. Now that's a simplified definition, and the simplified definition is simplified because I said it was non-negative. If you have a general function like this, if you want to allow the function to be negative, the function f of x to be negative, then the area, or then the, let me just highlight this, by the way, area. If you allow the function f of x to be negative, the definite integral a to b f of x dx is what we would call the net area. Between the curve and the x-axis between A and B. And what's that mean? What does the net area mean? Well, the net area is going to mean that when you draw it, I guess I'll draw a picture right here. So like, let's say your curve does this. That's what your curve does this time. And let's say we put the A here, and then we put the B here. Then the net area is going to be this. You calculate this area here, and you calculate this area here. And what happens is the area above the x-axis, which is here, above the x-axis counts positive, and below the x-axis counts negative. So let's just put that here. So area above the x-axis counts as a positive number. And area below the x-axis counts as negative area. Now, areas are not negative, but you can take the area and you could add a minus sign out front, and that's what we're talking about. Okay, so like, yeah, we'll see that. We'll see that momentarily. So that's the idea. Okay, now that's what it is on a graph, but that's not actually like, how are you going to formally define it? So more formally, but not completely formally, because again, I said this is a little bit tricky to define, but more formally, but not still 100% formally. What you do to get this definition is as follows. If you take a curve like this, and you have your A, and you have your B, like this, and if you divide this A and B, so if you divide A to B into, I'll say, in what we call subdivisions, that just means chop this up like this, basically. Divide A to B into n subdivisions. All right. Then I'm going to draw in rectangles on here, which you'll see in a second as soon as I'm done writing in rectangles on the graph. I mean, it's not going to be in for us. You're just going to be some rectangles. There's a lot of ways to do this. I'm not going to be able to do this, you know, super pretty because I drew way too many rectangles to make this a time-efficient process. Actually, I want that one not there. Okay, so I'm drawing in all these rectangles, and those rectangles each have some area, and you can add up the area of the rectangles. So, of course, you can say that the area under the curve is like this. So the integral from a to b of f of x it's not equal to those rectangles, but it's approximately equal to those rectangles, right? Now, how would I write the area of those rectangles? Well, each one has a width, and I'm going to say they all have the same width, and I'm going to call that delta x, which is hard to see there, but little triangle x, triangle X, triangle X, triangle X. They're all triangle X, which is delta X. Okay, so they're all the width times the height. Well, how are you going to get the height? Well, if I did this right, then the height is going to come from a y value on the graph. Okay, and so what's going to happen is you're going to get the area of those rectangles is going to be something like the width of the first rectangle is delta x. The height of the first rectangle is f of like the first x value, whatever that is. So like if I start numbering these x values here, maybe I can come in here and actually do that. Like this one could be x0, x1, x2, x3, and so on. If you number the x values like that, then the area of this of the rectangles is a width times a height plus a width times the next height plus the next width times the next height, like that. And you just do that all the way up until you get to the last rectangle, which the way I drew it would be n minus 1. That doesn't really matter. So for shorthand here, they use what they call summation notation, which you're going to see a lot in Math 4B. And so if you want to write that out without writing all of that, what you do is you use this symbol called a sigma, and then say, because each of these things here, each of these terms looks the same, right? So you have like a delta x, f of x0. They're all f of x something, right? F of x something, delta x. They all look like that. And then the I there, the first one was a 0 and the last one was an n minus 1. That's how you denote that. And what the sigma means is sum. So this means sum, or just add up. So add up. And so this what I wrote there is just shorthand notation for what I wrote above it in purple. Okay? And so what we have is this. Okay? Now, it's only approximate, right? Like the area of the rectangles that I drew on this picture are not actually going to be an area like this, right? If you draw a rectangle on here, like the rectangle doesn't match up perfectly with the function, right? Of course it doesn't. So that's why I wrote an approximate here. But then if you wanted it to be equal, you can define it this way. You could say, but we can actually define the integral with a similar formula like this. Where if you wanted to make the approximation better, then you would use more rectangles, right? I didn't draw very many rectangles. Well, I drew a lot of rectangles actually there. But like if you imagine, if I only used 2 rectangles like this, that's not a very good job approximating the area, right? It's better to use a lot of rectangles like I did here than just a couple like I did here. And so if you wanted to make the approximation better, you use more rectangles. Well, what's the most rectangles you could do? You could do 50 rectangles, that's good. But then you could do 100 rectangles, or 1,000, or 1,000,000, or 1,000,000,000. If you used 1,000,000,000, you know, how would you tell the difference between your answer and the real answer? You wouldn't. And so if you wanted to make a definition, you would do like an integral as n goes to infinity of this thing. So that would be like infinite rectangles. So like you go from this picture to, you know, more rectangles, which does a better job, right? You can see that. And then you do infinite rectangles, and what would that look like? Well, they'd be so skinny you can't even see them, right? If you used infinitely many rectangles, and that's how you get the exact area. So you have to take a limit there in order to get the exact area. And like I said, this is still not quite the precise definition because you can't just pick these x values any way you want and have that work out. So that's why I say it's more formally, but not 100% formally. Okay. Now, what are you going to be using this formula for? Nothing. Okay, that's just where it comes from. Okay, so you estimate the area with rectangles, and then you use infinitely many rectangles, and that's what the definite integral is, formally. But for us, right now, it's literally just this area. Okay? And so in this section, what you're going to be doing is not really calculating them with any kind of fancy techniques. You're going to be using geometry, right? Like, you know how to find the area of certain shapes, right? So, of course you do, right? Recall. What's the area of a rectangle, right? Length times width. That doesn't say width. What's the area of a triangle? Right? 1/2 base times height. And what's the area of a circle? Pi r squared. Right? And so what you're going to do is you're going to use formulas like this to actually calculate areas on your picture. And that's mostly what you're going to be doing in this assignment. Okay, so let's see here. I don't like these questions, so I'm going to skip them. I don't like that one, so I'm going to skip it too. All right, yeah. So here's an example. I would prefer to start with an easier one, but I'm not seeing it. So 0 to 3. Integral 9 minus x minus 3 squared dx. Okay, so we're supposed to evaluate this. Now, you don't have a way to do this with algebra, okay, or calculus. We can't solve with calculus right now. Okay, so what you're supposed to do is you're supposed to use geometry. Formulas. Geometric formulas. How are you going to do that? Well, let's look at the curve, okay? So what I'm going to do is I'm going to say they're asking you to find the area under y equals square root 9 minus x minus 3 squared between x equals 0 and x equals 3. That's what you're being asked to find. Now, what you may or may not recognize is that that curve, y equals square root 9 minus parentheses x minus 3 squared, is the equation of a circle. So let's see if we can do that. So let's look at like Desmos here. Graphing calculator. Y equals, we need a square root. Under the square root, we have 9 minus parentheses x minus 3 close parentheses squared. Okay, so you see what's going on, right? We've got this curve. So you graph this curve here. Try to make that a little prettier, darker anyway. So that's the curve that you're trying to calculate. And so draw a picture here of this. And what do we got? Up here at 3. 3, 6. It looks like 6. And then perfect. Okay, so that's my curve. Okay, so that's the curve that we're trying to find the integral of. But we're specifically looking for an area. So they say between x equals 0 and x equals 3. So what is that area on this picture? It's right there, right? So the integral, this area is equal the integral from 0 to 3 of square root 9 minus x minus 3 squared. Okay, that's what it is. But how are you going to calculate that area? You should just be able to recognize that that's a quarter of the circle, right? Like if you drew the rest of the circle in, that's literally just a quarter of a circle. So it's just equal to 1/4 the area of the circle there. What's the area of a circle? Pi r squared. But what's the r? The r is the radius. You should be able to tell that the radius, right, is 3. 3. So pi times 3 squared. So 1/4 times pi times 9. So 9/4 pi. That's the answer. Okay, so that's how you're going to be calculating areas in this section, is just with geometry formulas. But in order to use the geometry formulas, you need a picture like this. Okay, so if they don't give you one, then you're going to need to produce your own picture. So use a computer if you want to help you, or you could know that this is the equation of a circle. But it was just easier to use Desmos for that, so I did. Okay, and that's what we're doing here. We're calculating integrals by calculating areas, because areas are integrals. That's it. All right, let's do a different one. Okay. Give me a picture. Oh, you're making me sad. Okay, I'm gonna have to go back and come back. Oh, come on, that was 4 in a row of the same exact question. All right, 5 in a row of the same exact question. How could that possibly be true? This homework is playing a joke on me right now. It's refusing to give me the questions that I know are in this homework assignment. Yeah, all right, so I literally just want the whole assignment without giving me the problem. Insane. There's no way to pause. All right, well, I'm just going to make one up then, because this is ridiculous at this point. So I don't know why it's not doing it now, even though it was just giving me problems that I skipped. So I'll have to make one up here. So there are problems like this, I swear, where they give you a graph of a function, and they're going to draw some circles on there, and they're going to draw some triangles on there, and that's what they're going to give you. And then what they expect you to do is calculate those with formulas. Okay, so let's, all right, I'll just draw it. So I was talking again just to try to make it do it. One, two, three, 4. We'll put a 4 there. So they go like this, and they say that that's f of x. And then they'll go like 4, 5, 6, 7, 8. 8, like that. And then they'll go like that. And then maybe they'll do like, I don't know, one more triangle or something. Which I guess that would be 12 there. And then they say that's F and that's G and that's H. And then they say they want the integral of that thing. And they don't give you bounds or anything, which is why it's a little bit weird. But what they want you to do is just add up the areas of the pictures that you see. And that's it. And I'm still like talking really slow and clicking through the problem because I just really wanted it to give me one of these so I could make sure I knew what we were doing, or they knew what we were doing. Everybody knew what we were doing, and they just won't do it. All right, well, we can't. Okay, so let's say this. So let's say they just say, they say like find the definite integral of all three functions or something weird like that. Find the definite integral of all three functions and add the results. Okay, and I have literally no idea why they are not letting me just find one of these problems in the homework. But it's pretty easy. So like technically the integral, I'm just going to write them out for practice here. So this is 0, right? So this area right here, that's an integral from 0 to 4, right, on the x-axis. That's where those numbers come from, of the function f of x. Okay, now the next one is here. That's going to be the function from 4 to 8, right? Those are the numbers on the x-axis of g. And then the last one, this area, that's going to be an integral from 8 to 12. Again, the numbers on the x-axis on the left and right sides, and the function would be h of x. Okay, so that's formally what that is. Now, how would you calculate that? Well, the way you would calculate that is just with the formulas for the areas of a triangle and the areas of a circle again. So what you were expected to do is this. So like for the first one, f is a triangle. So the formula is 1/2 base times height, right? 1/2 base times height. So you go 1/2, what's the base? The base is going to be 4, right? What's the height? Well, the height looks like here, so it's 3. Okay? Then you move on to the next one, which is going to be the area of a circle. But how much of a circle? It looks like a half circle. So it's going to be 1/2, like it's going to be 1/2 and then pi r squared, right? So we have the 1/2 pi. What's the radius of that circle? You have to make sure you can tell what the radius is. The radius is not 4, right? Because you measure from the center over, so the radius is 2. So 1/2 pi 2 squared. And then we get to the last one. That looks like another triangle, so it's another 1/2 base times height. So 1/2 base height. What's the base? What's the height? Well, again, the base is 4. I made them all 4 for some reason. And the height, what's the height? Oh, it's 3 again. Interesting. So you add up the areas there, and those areas are going to be those integrals. So you just add them all up. So 1/2, 4 times 3. 4 times 3 is 12, times 1/2 is 6. Next one is 2 squared is 4, right? 2 squared is 4, times 1/2 is 2, times pi, so that's 2 pi. last one, another 1/2 4 times 3, so that's another 6. So the result here is 12 plus 2 pi. You can't simplify that because 12 is not like terms with the 2 pi. So you just write 12 plus 2 pi and then that's your answer. Okay? And really, you should have some of these, and I don't understand why you don't. Okay, anyway. So let's move on. So what's next? There's only one other topic in here, and that topic is going to be for the very basic rules of antiderivative. Sorry, the basic rules for definite integrals. So rules for definite integrals. Kind of like the rules for indefinite integrals, but there's more of them here because we have limits of integration to deal with. So first of all, if you're doing an integral of an f plus a g, you can split that, just like you can for indefinite. You just keep the limits of integration. Okay, so that's one rule. Also, if it's a minus, then it's a minus. The next rule is going to be the scalar multiple rule, which you also know. If you have a constant times a function, the constant can come out of the integral. So this is just the same rule that you've already seen, right? For indefinite integrals. But now you can do it for definite integrals. Now after this, then we're going to get to the rules that involve the limits of integration. Okay, so kind of like these are kind of old rules that are up there, but now we got some new ones. So the new rules are going to be these. So you have one rule that says if you have a definite integral from a to b, that's actually the negative of the integral if you switch those. So I put the a on top this time. So switching the a to the b is going to switch the sign on the integral. Right. Basically what it does on the picture with the rectangles is if you switch the a and the b, whatever way you were coming up with the number delta x is now going to make the delta x a negative number. And so everything's the same except you added a minus sign. So switching the a and the b just literally adds a minus sign. Okay, so that's a rule. And the other rule we need, you actually have already seen even though you didn't know it. So think about this. I had three functions just next to each other, right? And I wanted the total area. And so what I did was I did an integral from 0 to 4, then 4 to 8, and then 8 to 12. Well, if you think about it, if you go 0 to 4, 4 to 8, 8 to 12, then I actually went all the way from 0 all the way up to 12, right? Like I started at 0 and ended at 12. So all of this together is basically just the integral from 0 to 12. And that's a rule. So the rule is this. If you do an integral from a to b, and you add it to an integral from b to c, that's equal to an integral from a to c. And we'll draw the picture for that one, even though we just talked about it a little bit. So, pretty simple idea. If you have a to b and then b to c, right, and you split that up, if you take this area, which is that, and then you take this area, which is that, right, a to b and then b to c, if you add those together, aren't you just going to get the integral from a to c, which is from here to here, right? A to c. So that's all the rule says. Very simple rule, makes perfect sense. You go A to B, B to C, you get A to C. Okay? Now, you have a couple of questions where you have to use these rules. All right? And they're very easy, I think. They might be confusing at first, but I think they're easy. And they go like this. So like example, they say 0 to 2 of 7f of x minus 6g of x dx. We're supposed to find this. Find this. Okay? Given, and then they give us a bunch of information. So they told me the integral from 0 to 14 of f of x. Really? Why would they do that? Is 9. They tell me the integral from 0 to 2 of f of x dx is negative 9. They tell me the integral from 0 to 14 of g of x dx is 5, and the integral from 0 to 2 of g of x dx is 3. Now they're giving us twice as much information as we need here. I don't know why, but probably because this is from a book, and the book does more than one problem with the same information. But this is what they gave us. So here's what you're supposed to do. So just start with what they gave you. Start with what you want, I mean. Start with what you're supposed to find, which is 0 to 2, 7 f of x dx minus 6 g of x dx. Dx is there, actually. Okay. So what are you supposed to do? You're going to apply the rules. So one rule says you split this up. So we apply the rules. So first thing we're going to do is we're going to split this up because it's a sum. So this could be the integral of 0 to 2, 7 f of x dx minus an integral from 0 to 2. You keep the same limits and everything, of 6 g of x dx. Okay? So we split it up using one of the rules. Now, then what you're going to do is you say, okay, well, I've got a 7 here and I got a 6 here. And there's a rule that says I can take those out, right? Like the second rule says if you have a constant, you can take the constant out. So you take the constant out front. So you take the constant out front. So that's the constant multiple rule. So you have 7 integral 0 to 2 f of x dx minus 6 integral 0 to 2 g of x dx. All right. And at this point, what you want to do is you want to just use the numbers that they gave you, because they gave us these actually. Because right here I have an integral from 0 to 2 of f of x. Now look up here. Where is that? Here it is. 0 to 2 of f of x is negative 9. So I know this is negative 9. Of course, you still have the 7. Then what about this other one? What about this one? 0 to 2 of g. Well, what's the integral from 0 to 2 of g? Again, you're just looking it up. So 0 to 2 of g looks like it's right here. That's 3. So you put in a 3, and then you just add this up. So of course, this is simply going to be 7 times negative 9 is negative 63 minus 18. What's that? 81, negative 81, I think. Yeah. Okay. So they're not really like, on this kind of question, they're not giving you the picture, they're giving you numbers, and you're supposed to use those numbers to perform the calculation. I think they're very straightforward. They do give you numbers that you don't need. Let's do another one of those, and I think that'll be it. So let's see. We want find 0 to 2 again for some reason. Negative 4 f of x minus g of x dx given, and again they're going to give us a whole bunch of stuff. We don't need all of it, we only need 2 of them. They tell me 0 to 17. You can probably already see we don't need that, but it's negative 7. 1 from 0 to 2 of f of x dx, that's 6. 1 from 0 to 17 of g, that's 6. And 1 from 0 to 2 of g, and that's minus 2. All right, so just like the last one, so these are very straightforward. So we got 0 to 2, negative 4, f minus g. So what do? You're going to split it. 0 to 2 of negative 4f minus integral 0 to 2 of g. Then you can use the constant multiple rule. We only need to use it once this time instead of twice. So just right here, take that negative 4 out front. And then finally, we're just going to look these up. So I've got 0 to 2 of g, 0 to 2 of g. So that's minus, looks like minus 2. The other one, 0 to 2f, here it is, 0 to 2f is 6. So that's negative 4 and then 6. And then we just add this up. So negative 4 times 6 is negative 24. Minus 2 is plus 2. So negative 22 it looks like. Yep, and that's that. Okay, so that's that assignment. Now I do want to be clear about something before we move on. This is not the way you're going to be doing definite integrals, okay? So you do it for this assignment because this assignment is just calculating areas, okay? In the next assignment, it's going to be very important. It'll be calculating these with the method that everybody uses. So next lecture is the fundamental theorem of calculus. It's important, that's why it's called the fundamental theorem of calculus. Next lecture, fundamental theorem of calculus. Among other things, it gives us a better way to do these. This is how you actually evaluate integrals. So how you actually solve these problems. So don't miss that. Okay, so that's it for now. Talk to you guys later.